Welcome to the last lecture of the course CST 301 Formal Languages and Automata Theory. In this lecture, we are going to see a decidable problem about Turing machines known as the halting problem, and we shall also prove that this problem is undecidable. So the topic for today is decidability and halting problem. So we shall see the halting problem, and we need to prove that the halting problem is uncomputable. So before we look at the halting problem, let us see what is the notion of computability using Turing machines. A mathematical function from a set A to a set B is said to be computable if there exists a Turing machine F which, when given with an arbitrary element of the domain set, will halt in the accept state T with the value of the function for x, f of x, as the non-blank content of the T. So what we are saying is, a function f, small f, is said to be computable if and only if there exists a total Turing machine capital F, which is, when given with an arbitrary input in the domain, will halt in the state T, which is the accept state, with the non-blank state content the required value of the function. So for any x, it computes f of x and stops in the accept state. If there exists such a Turing machine, then the function is said to be computable, and if there is no such function, the function is said to be uncomputable. Example computable functions: a function from natural numbers to natural numbers, and the function is defined as, for all x, f of x is equal to x plus 1, which is the increment function. And we had designed total Turing machine for this function, and hence by this definition the increment function is computable. Another function, given a pair of natural numbers, it finds the sum of the natural numbers. F of x plus y is equal to, f of xy is equal to x plus y. So it is taking two natural numbers as input and produces their sum. And we have designed a total Turing machine for finding the sum of two numbers in unary representation, and hence by this definition the function to find the sum of two natural numbers is computable. And I have given you a homework exercise to design a Turing machine to perform multiplication, which can be used to find the square of a number. And you can design a total Turing machine which always halt in the state T by producing the square of the number in the unary representation as the non-blank content of the T. And hence by definition of computability given here, this function is again computable. And you can see that most of the interesting function in practice is computable. Now, being defined the notion of computability. So it's said to be computable for a general problem. And if you are looking at problems whose outcome is either yes or no, those problems are called decision problems. And for decision problems where the outcome is either true or false, computability is also known as decidability. So when the problem is having either yes or no answer, the notion of computability is known as decidability. Okay, now let us recall the possible behaviors of a Turing machine on a given input. Let M be a Turing machine and X be an input string to the Turing machine M. Then what are the possible outcomes of computation of M on the input string X? This is the first possibility, where when the machine M starts executing the machine or executing the input, when the tape content is left hand marker followed by the input followed by blank symbols in all the other cells, eventually it gets into a configuration where the state is T. We know that T is a sync state. Once the machine gets into it, it can never move out of it, and when it gets into such a configuration, you say that the input string is accepted. And in case 2, it gets into the sync state R and the string is said to be rejected. So these are two possible outcomes. The string is either accepted or rejected. In both the cases, we can say that the machine halts on the input string X. If you recall the definition of halting that we discussed in a previous lecture, this is exactly the definition. If the Turing machine either enters T or R, then the machine is set to halt on that input. And there is a third possibility, and that also we discussed. Suppose looping happens. This is the same example that we discussed. From this configuration, what is it saying? If the state is P and the input symbol is small a, change the state to Q, replace the small a with small a itself, retain that symbol and move right. That's what you did. And here the transition function wants you to change the state to P when you are reading small p from Q, and retain that symbol and move left. So you are going back to the LHS configuration, and this will happen forever. So the machine in this case is neither getting into T nor getting into R, and in this case the machine is set to loop on the input string X. Okay, so there are three possible outcomes. One is the input string is accepted by entering the sync state T. Second case, the input string is rejected by entering the sync state R, and these are collectively known as the halting outcome. That is, the machine halts on X, and the other possibility is the machine loops on X. Okay, these are the two possible behaviors: M halts on X or M loops on X on a given X. Now we can define the halting problem for a Turing machine. It is the problem of checking whether a Turing machine M halts on an input Y. See that given an input, the machine either halts on the input or loops on the input. These are the only possibilities, and the problem is to check whether it halts on a given input or not. Is the halting problem decidable or computable? Answer is yes, only if there exists a total Turing machine for solving the halting problem. That is the notion of computability that we defined in this lecture. So it is decidable only if there exists a Turing machine which is total for solving the halting problem. That means that Turing machine will take, the Turing machine is assumed as capital A, that will take the Turing machine M and an input Y to M as input, and will say whether M halts on Y or not. Okay. Now, is there exists a Turing machine A for solving the halting problem? If there exists one, so this is how it looks like. And what is it taking as input? It is taking a pair of binary strings separated by a hash. From the previous lecture, I think you remember binary encoding of a Turing machine. Here, X is a binary encoding of a Turing machine, M. And the notation is the Turing machine M, which is denoted or encoded as a binary string X. And Y is a binary input to this Turing machine. This is not an encoding. What we are taking is a binary input to the Turing machine. And so what is this notation MX? It is a Turing machine M whose binary encoding is X. So if you are assuming that the halting problem is decidable, then by definition of decidability or computability, there exists a Turing machine A which takes as input a binary encoding X. X is a binary string, which is an encoding of a Turing machine M, and the notation MX stands for the Turing machine M whose binary encoding is X. And what is the other input? Which is a binary input to the Turing machine. Not that it is a binary input and it is not the encoding. That is what we are taking. And it is also logical to assume that an input is binary because you know that any object can be represented in binary. Now the question is, can you use the universal Turing machine in place of A? It looks like it is possible because the universal Turing machine is taking the binary encoding of a Turing machine and an input to that Turing machine as input, and it runs that Turing machine on the input. Now the question is, can the universal Turing machine act as the Turing machine deciding the halting problem? We can see. Recall the behavior of the universal Turing machine from the previous lecture. I hope you remember it. And what is it doing is, it accepts its input if the Turing machine MX, that is the Turing machine whose binary encoding is X, accepts the input string Y. And U rejects its input if MX rejects Y. And U loops if MX loop on Y. So this is exactly the behavior of the universal Turing machine. I hope you remember it, otherwise please refer to the previous lecture. So in the first two cases, you can say, the universal Turing machine can say MX halts on X, because if it either rejects Y or accepts Y, you can say that MX is halting on Y. But in the third case, the universal Turing machine cannot say whether or not MX halts on X, because maybe MX is processing by utilizing the infinitely many cells on the tape, moving all the way to the right, left, etc. It cannot just finish after a finite amount of time by guessing that the machine is looping. That can never be done, because maybe later on it's going to halt, enter either T or R, accepting or rejecting. So that is the difficulty, right? So universal Turing machine cannot solve this problem. I hope you are getting me. Now we can look at this theorem by Turing, Alan Turing, who stated and proved it in 1936. And what he proved is that halting problem is undecidable. So no one can have a total Turing machine deciding the halting problem or finding the solution for the halting problem. What is the halting problem? Given a Turing machine M as its binary encoding X, and a binary input y to the Turing machine M. Check whether the Turing machine M halts on y or not is the halting problem. And Turing proved that it is an undecidable problem. And he has proposed a proof by contradiction by utilizing the diagonalization technique. So, for the purpose of contradiction, assume that halting problem is decidable. So, what is the assumption that we made? There exists a total Turing machine A which solves the halting problem. So, what is it taking as input? It takes as input the binary encoding X of a Turing machine M. So, X is the binary encoding of a Turing machine M. And it takes a binary input to M. Not that Y is not a binary encoding, it is a binary input to the Turing machine represented by the binary encoding X. And what it says? It says either H or L. What is the H means? Mx halts on Y. That is the Turing machine M represented by the binary encoding X halts on its input Y. L means Mx loops on Y. So if you assume that halting problem is decidable, this is exactly what you are assuming. So given an arbitrary input string X, Y over the alphabet set 0, 1 hash. X is a binary string, Y is a binary string separated by a hash. And what is X? X is a binary encoding of a Turing machine M, denoted as Mx. And Y is a binary input for M. Recall that Y is a binary input, not an encoding. And what A will do? A will halt and say the output as H if Mx halts on Y. And it will halt and say L if Mx loops on Y. So that is what A is supposed to do. Now you look at the behavior of the assumed Turing machine A on all its input. And what is the input to the Turing machine A? It is the set of all Turing machine encodings and the set of all binary strings to the Turing machine encoding. So here a row represents a Turing machine encoding. For example, 001 represents the Turing machine whose encoding is 001. Now you may have a question, can 001 a valid encoding for a Turing machine? If you look at the binary encoding we discussed, no, it cannot be an encoding. We will consider that case. Okay. Anyway, a row represents a binary string, which is nothing but an encoding of a Turing machine. And what is a column represents? A binary string to the corresponding Turing machine, which is going as an input. Now, for each binary string X, let Mx denote the Turing machine. Okay, what is Mx? What is M01 for a binary string 01? What is it representing? It represents a Turing machine M if X is the binary encoding of M. Okay, if X is a possible binary encoding for M, for a Turing machine M, it is representing that machine. In the other case, that is, if the binary string like this is not a valid encoding of a Turing machine. In the previous lecture, we have seen a finite state automaton for checking whether a binary string is a valid encoding of a Turing machine. So you can easily check it. If it is not a binary encoding, what you can do is you make it a valid Turing machine which loops on all its input. It could be just a one state Turing machine. In that state it loop. Okay, just a one state Turing machine which is not the state T or R. Then that means it will always loop regardless of what the input is. Okay, so without loss of generality, assume that every row here represents a binary string which is an encoding of a Turing machine. In general, that is not true, but you can then consider that as a Turing machine which loops on all inputs. Now, what is a table entry? It is for an mx and a binary string y. For example, here m11, x is 11 and y is 011. And what is an entry? That is the outcome of the assumed Turing machine A. What are the possible outcomes? H or L. L means mx loops on y. H means mx halts on y. So the entries of this table are H or L. Every entry is H or L. For example, if you are looking at that particular Turing machine, for every input x, which is a binary encoding of a Turing machine mx, and a binary input string y, H means mx halts on y, and L means mx loops on y. Now we assume the existence of such a Turing machine. So definitely, given an mx and any input string y, it will either say H or L, and that is why every entry in the table is either H or L. And it doesn't matter what is it, L or H. Randomly I have given some values L or H. Okay, it doesn't matter. Now I am going to construct another Turing machine B from this A. By utilizing A as a sub procedure, I am going to construct another Turing machine. This is that construction. What I do is, I am giving x hash x as input. What is x? X is a binary string. So the same binary string is given here as well. So what is it representing for A, for this Turing machine? Mx is the Turing machine that it is taking as input, right? It is an encoding of a Turing machine, and x is a binary string, not an encoded string, binary string which goes as an input to the Turing machine mx. Okay, and then it just runs A, and A is assumed to halt and say H or L. Okay, and what is H saying? Mx halts on x. Then this Turing machine is B is going to loop. That is, if A is saying H, what I will do in B is I will enter a looping state. Okay, you can manage it with the two states. You just loop there. Okay, and if the Turing machine A says L, that means mx loops on x. Then what I will do is I will immediately enter the state T. That means when A says H, I am entering a loop in B, and when A says L, I am entering a halt state. Okay, so what basically I do is, if mx halts on H, then the machine B is looping, and if mx loops on X, then the machine B is halting. Okay. Now, what is this? What are these rows in the Turing in this table? It is the set of all binary strings, right? It is representing the binary string epsilon, binary strings of length 1, binary strings of length 2, etc. It goes. So it is an infinite table where each row is a binary string. So every binary string is listed over there, and hence every Turing machine is listed, because every Turing machine is having a binary encoding and every binary string is listed over here. So every Turing machine is listed. Now we are going to derive a contradiction. We are asking this question: is there any binary string or row X such that Mx is nothing but the constructed Turing machine B, or we are asking whether exists a binary string which is an encoding of this Turing machine. It must be the case, right? B is a Turing machine, and in the previous class we saw that for every Turing machine there exists a binary encoding. So definitely there must be a row X representing the Turing machine B. But we are going to prove that it is not there, and hence a contradiction for this assumption that there exists a Turing machine solving the halting problem. You can see that the machine B at least differs from every Turing machine listed over here in the diagonal position. So if you look at any diagonal position, here I am looking at here. So what is the input to the Turing machine A? X mx, right? Mx is the Turing machine given as input, as the binary encoding of the Turing machine is 001, so the machine is mx, m001. And what is the second string? It is unencoded binary input, which is 001. So actually we are giving the diagonal case as input to the Turing machine M. And what is it doing? Suppose the original machine mx halts on 001, it is the case, then the machine B is looping. So M001 is not B, because for B you need here L as the outcome, because that is what you did. The original machine mx is halting on X. In that case we made B looping. So it differs in that position. And you can see that it differs at every diagonal position. For example, suppose this is the original diagonal values computed by the machine A. What the machine B is doing, if it is L, then B is halting because it is entering the state T. If it is H, this is the outcome, then the machine B is looping. So exactly the machine B behaves differently, at least in the diagonal position. So we can say that at least in the diagonal position the machine mx differs from B for every binary string X, and hence existence of A to solve the halting problem is a contradiction, because B is a Turing machine and there exists a binary encoding for that Turing machine. That is very clear. But we are getting a contradiction because we are proving that no binary string can represent B. That's a contradiction. And thus we proved that the halting problem for Turing machine is undecidable. With this we are finishing this lecture. Today we discussed about the halting problem for Turing machines. And what is the problem? Given a Turing machine encoding and a binary input to that Turing machine, decide whether the given Turing machine represented as a binary encoding halts on the binary input or not. We proved that it is not a decidable problem. There cannot be a Turing machine deciding this problem or finding the answer to this problem for an arbitrary input. And the notion of computability or decidability that we define today is that a mathematical function f is said to be computable or decidable if there exists a total Turing machine which computes the value of that function for every possible input. And we define the halting problem and prove that there cannot be a total Turing machine solving the halting problem. With this, we are finishing this lecture, and we finished all the topics included in this course. Thank you. Thank you for attending all the lectures, and I hope my video lectures is helping you to learn the course formal languages and automata theory. Thank you.